Hello class, in this video I am going to show you what you need to do specifically in Excel for the third problem set homework. So what I did here is I took some screenshots of each of the four questions and copy and pasted them into an Excel workbook where each question is a separate worksheet in the workbook. So this is what I advise for you to do for your homework as well. So this first question is actually one of the easier ones. It's asking us to compute a confidence interval for the mean, given a sample of numbers, and it's actually two samples because we have to change one of the numbers. So what I did was I took the first set of numbers here, made a column, and then I made a second set of a second column here with the same numbers, knowing that we had to change this one outlier of 139 and change it to 29. And why is that an outlier? Because it's significantly bigger than the rest of the numbers in the array. And the general rule of thumb is if an outlier is generally 1.5 times larger than any number at quartile 1 or quartile 3. And this number clearly meets that benchmark. So to do the confidence interval for the mean, all you need to do is use your handy dandy data analysis tool pack, and it's under the data ribbon up top here. You go over to data analysis, you go over to descriptive statistics, click OK. And we need our input range, and so obviously we're going to have to do this twice. So we're going to highlight our data. It's in a column. There's labels in the first row, and it's asking us where we want to put it. You can either put it in a new worksheet. I put it in the worksheet that I'm working in, so I would click output range, and in this box I would just click over here. And then this is the most important part. You got to click the summary statistics because that's going to give us our mean, and then the confidence level for the mean. In this case we know that it's asking us for 95%, so we'll leave that in, and then you just click OK. So there's our numbers for the first array, and what you need to pay attention to here is the mean, which I have highlighted here in blue, and then down at the bottom of the output it says confidence level. So this is our confidence interval. So what you need to do is take this number, I got highlighted here, and subtract it from the mean and add it to the mean. So all I did here, and this gives us our lower and upper limits of the confidence interval, is did a little formula here. Is just subtracting this number from the mean and then adding the number to the mean. And I did it for the first column, the outlier group, and then the second column for the no outlier group. And your task for this question is look at the difference. Does it affect the confidence interval? I'm pretty sure it does, as you can see. Alrighty, so that's question 1 done. Question 2 is a little more tricky, and it's because Excel kind of sucks in that it doesn't have a built-in analysis for a one sample t-test. So we kind of have to use the manual formula, and the formula up here is given to you, and it's really kind of easy. It's the sample mean minus the target or population mean divided by the standard deviation, which is further divided by the square root of the sample size. And note here the order of operations. You're going to have to compute this bottom part, the denominator, first to get the square root of the sample size, and then have the standard deviation divided by that before you divide the difference between the sample and the target mean. So it helps to put your numbers, pull them out of the problem, which I did here. So I got my sample here, I've got my means, and I got my standard deviations. So using that, I built a formula up here, okay, and it's saying that M5, which is the mean, this is given to you, $315.40, subtract 300 from it, okay, again divided by the standard deviation, which I have typed in here in M6, divided by the square root, and that's a function, SQRT, of M4, which is up here, the sample size. And so what that you need, that's the first step. So that's your calculated value. You have to take this calculated value and then generate the critical value from the t-table. And you don't need to look this up. Excel has this stuff pre-programmed in. and it's using this t dot inverse formula function. So if I click on this, I'll show you what it looks like, and you just input the numbers. Okay, so we put 0.9 because it's asking us for a significance level of 0.0, so we know to take the difference, which is 0.9, and the degrees of freedom, well, that's simple. That's the sample size minus 1. So we know the sample size is 25, so we just put in 24 here. We get a formula result of 1.317. So to interpret that, I kind of gave you that here. It says here, since the calculated value, t-value of 1.78 is greater than the critical value of 1.317, we can reject the null hypothesis, okay, and conclude that there's evidence that the population mean is above $300, okay? And then you would just repeat the same for B and do the comparison between the calculated t and the critical value. And notice though it's asking for a different p-value of 0.05. So when you do the formula here, note that your t inverse should be 0.95 instead of 0.90. For C, same formula, except the standard deviation is now changed. It is now 43.2 instead of 75. And then for the last part D, I wrote in here, don't forget to write something, because a lot of people forget to do that. So based on the information in part A, what decision should the director make about books? You should make your decision based on the results that are given here, okay? Question 3. Okay, this is very similar to the last problem, except so you got to kind of know the notation, if you will, for when we say decision rules. Okay, this is when we talk about hypothesis testing. You always have a null hypothesis, and then you always have an alternative hypothesis, and your null hypothesis is always going to be there. It basically means there's no difference, okay, in whatever you're testing for or comparing, okay. Your alternative hypothesis basically is your hypothesis. It's basically saying something is either less than or greater than or different from something else, okay. So in research methodology notation, you call that the HO, okay, for the null, and the HA, or some people call H1, for the actual hypothesis or alternative hypothesis. So in our case, we know our null is a given. We know it's equal to 100, okay, because it means there's no difference between the mean. And our alternative hypothesis or actual hypothesis is that the mean is different from 100. And we're not specifying a direction here, and this is important, because this is when we start talking about one and two tail tests. Typically a one tail test is when you have a hypothesis that is, you're saying, if this in this case it would be, you would conclude that the mean is less than 100 or greater than 100. And in either of those cases, if you say that direction, then it's a one-tail test. Since we're not specifying any direction, we can say it could be greater than or less than, we're just saying it's different. It's what we're referring to as a two-tail test, okay? And that's important when we're looking up the critical value from the t-table, which I'll show you in a second. So like before, we need to know our mean. I didn't bother with the data analysis tool pack this time, although you can use it for simplicity purposes, but I just use standard syntax here, function syntax, to get the average or the mean, which is here. I did it again for the standard deviation, and I did it here for the square root instead of using that equals or embedding that into the formula. So see here, I have our initial formula, so our calculated value of 4.719 or 4.72, okay, and then I have our critical value from the t-table. Now this is where what's important. This is where you see this similar lookup of the t.nv, but notice it says .2t. That's that two-tail test I'm talking about here, okay. So this dialog box looks very similar, okay, and I put in my probability, okay, and I put in my degrees of freedom, because there's 6 numbers. Now remember it's sample size minus 1, it gives me 5, and so I have a critical value of 2.57, and our decision rule here is, since similar to the previous problem, since 0.72 is greater than 2.571, we can reject the null and conclude that there is evidence that the sample mean is different from 100. Now the p-value, okay? This is tricky, and I'm going to tell you, just look at what I did here. I used this function syntax up here. T.dist.toTail, so the 2t, and this ABS means absolute value of M17, which is my calculated t-value, and then my degrees of freedom. Now, something I put in here, something you should know. Don't forget to interpret. This question gave us a significance level of 0.05. Okay, you're going to be comparing this calculated p-value against 0.05. Ours is 0.005. That means it's less than, okay, 0.05. And when it's less than, that means our difference here, okay, is statistically significantly different, okay? And that's when you get a chance to say this. If this p-value was greater than 0.05, like 0.06, 0.10, 0.8, there would be no difference. It would not be statistically significant. So since our value of 0.005 is much less than 0.05, we can say that there is a statistically significant difference. Okay, last question. Sorry this video is so long. I just want to get all the problems into one video. Obviously you can pause and rewind to pick up where you left off. So this last problem, okay, I hem and hawed over this problem because it can either be a one sample or a two sample z-test to test of proportions. Okay, the solution key I was given has it as a one test, though I would argue it's a two sample because there's two figures you're comparing against here. So basically what this problem is asking is if the nationwide study of 50% is different than the UMUC sample of 48%. And how do I get those numbers? Okay, so we're given the 50%, okay, and again, remember our decision rule notation. We have a null hypothesis here, okay, and again, I want to point something out here. It says less than or equal to 50%. So a little bit different when I said there's no difference. Because this question here is asking, is the proportion of students at UMUC that change their major higher or greater than 50%? So is it making a directional statement? Okay, we know that our actual hypothesis is looking for a value greater than 50%. Therefore, our null hypothesis is not just that there's no difference, but it's also less than 50%. So it gives us a real easy proportion to calculate. 48 out of 100 gives us 48%. So our test here, our proportion test is this 48% different than 58%? Is it statistically different? Okay, so to do this test, you have to calculate a critical z-value. Okay, and this 1.644 is calculated using the norms inv function syntax. Okay, so if I click on the function box here, I put 1 minus 0.5 because it's asking we're assuming a 0.05 probability. However, just so you know, just look at this norm equals norm.s.iv in 1 minus 0.05. Just telling you what it is. It's not something you should know off the top of your head. That's just telling you that's how you get the critical z-value. We have a standard deviation of a population standard deviation of 0.05. Again, this was a pain in the butt to calculate, for you to know how to calculate, because usually that's a given. The formula there is the square root of 0.5 times 1 minus 0.5 divided by 100. Okay. I'm sorry. Some of this isn't intuitive or spelled out. If we had a textbook, maybe it would be, but we don't. And then we have our calculated z, which is a real simple formula. It's just our initial proportion minus the population portion divided by our population standard deviation. So I kind of spelled out the two formulas here in text form. So again, real easy to calculate for the calculated z. So the decision rule, if the z-value, okay, our calculated z-value is less than the table value of 1.664, you would not reject the null hypothesis. So the z-value of minus 0.40 is less than, therefore the decision is not to reject the null. Okay? All right, folks. Sorry, again, we have 15 minutes worth of video here. If you have any questions, just let me know, and I hope this helps.